I think I know what you're thinking. I thought I was looking at chemistry. This sounds more like physics, doesn't it? Electromagnetic radiation. Well, we are still studying the atom. The modern model of the atom is the quantum mechanical model, and you need to know a little bit about electromagnetic radiation. Most students don't have a very good background in physics, so I'm going to spend one video reminding you about the things that you have learned in physics, or maybe you didn't learn them in high school. This is not abandoning chemistry at all. This is material that you need to understand in order to understand the quantum mechanical model of the atom. Okay? So please bear with me. I know it's not a lot of fun, but we'll get over it. We begin talking about light. People have wondered what was light for a long, long time. In the 17th century, Sir Isaac Newton said, well, we know that light consists of many different colors that are combined together. You've seen light being diffracted by rain from a rainbow, or when it goes through a particular glass container and creates a little rainbow on your table. You know, light diffracts into all the different colors. He was right there. But he said that light was composed of streams of very, very little particles traveling at a very high speed, and they follow his laws of motion, which makes sense because that's what Sir Isaac Newton was known for the laws of motion. So he said, okay, light is made up of particles. And he did do some experiments. We're not going to get into all of that. There were experiments that seemed to prove that light was made up of particles. Okay. So this fellow in the 19th century, Thomas Young, said, let's see something else. Imagine you have, and I hope the tablet won't ruin me, you have a wall with two slits, and then you have like a screen reflecting. If light was made up of particles, this particle hit here and couldn't go through. This one will go through the slit, then this one couldn't go through, this one will go through, this one couldn't go through. So you see two bright spots for the two slits, and everything else will be dark. Okay? If light is made up of particles. Now he actually did it. So there we have the two slits. And what he ended up seeing here was a dark light, dark light, dark light, dark light. In fact, I didn't put it in here. I should have. Give me a second because I have a picture. You see, that's what he saw. That's more than two light spots. Agree? So he said, light is not made up of particles. The experimental evidence shows it has to be waves, because when you have a slit and a wave comes, some waves are going to pass, some waves are going to get diffracted, some waves are going to then interfere with each other. So he said waves could explain this pattern. It's not particles. So basically, what we have in here is some experiments that seem to show that the light is made up of particles. Some experiments seem to show that light is made up of waves. Maybe waves and particles are somehow connected, and we call it wave-particle duality. So light is made up of maybe both waves and particles, maybe some in between. Like I said, people keep going back and forth. I remember when I was a freshman, I took chemistry, and they said, oh, light is made up of energy, waves, sorry. The next year, I had botany. No, light is made up of particles. Wait a minute. Will you just make up your mind? It took me a good while to realize it wasn't that my professors didn't know. Scientists didn't know at the time. Yeah, like I said, it was people who favored one theory over the other. That's all there was to it. So before we continue, what is a wave? A wave is an oscillation or a periodic movement. We represent a wave like this. And a wave moves energy. Okay? Just like imagine this is a rope and you're grabbing here and you shake it. Or when you throw a pebble in the water and you can see waves appearing and all of that. it's important that waves transfer kinetic energy, but matter pretty much doesn't move. You have a little leaf flowing in the water, you throw a pebble in the water, when the wave comes, the leaf moves up and down, but it doesn't move towards the sides. Okay? So waves are energy. Waves can move not only through matter, they can move through the vacuum. But there's a particular type of waves, electromagnetic waves, that is what we're concerned about, that there are actually two waves that are moving continuously. You have an electrical field that has some waves, and then perpendicular to that, this will be coming in and out of the screen, you have a magnetic field. And what you're having is two waves perpendicular to each other and moving in a third direction. You have one wave moving up and down, another wave moving front and back, but they're moving from left to right. Okay? We're going to be dealing with them as if it was one wave, but keep in mind there's actually two sets of waves that combine together. Okay? When the electromagnetic waves travel through the vacuum, the speed is constant, that's the speed of light. And you need to know this number because we are going to be using it a lot. Okay? It's a really big number. Keep in mind 10 to the 8 is a very big number, and it's meters. Think on a meter is about a yard per second. Okay? So you're talking about hundreds of millions yards per second. That's mind-boggling when you think about it. To define a wave, there's a number of properties that we worry about. The wavelength is a distance between two consecutive peaks. So you have a peak here, a peak there, and that's the wavelength in here. The frequency, well, the wave by wave represented by the Greek letter lambda. Frequency, and this is wrong, I need to change it. Sometimes when I copy, the Greek letters become our Western alphabet, but that's supposed to be a nu. Okay? And that tells you how many waves in a particular period of time. That's usually a second. So the unit is going to be waves per second, second minus 1, also called hertz after the fellow who discovered that. And the amplitude tells you how high the wave is. If you look at the distance between the peak and the trough, half of that distance, that's the amplitude. Okay. Two things that I want you to keep in mind. One is that the frequency, when we're talking about light, okay, is going to determine the color. So the color doesn't, well, you can say the wavelength because that's related, but the amplitude tells you the intensity. Okay? The frequency or the wavelength, because they're related, will give you the color of a particular light. The other thing I want to mention is noise, that when you have a big wavelength, in a certain period of time, you can fit a very small number of waves. When the wavelength is smaller, you can fit more waves. So they're inversely proportional. Okay? So when we write as an equation, the speed of light is going to be the product of the wavelength times the frequency. Okay? C equals lambda times nu. I told you we'll say n in there, it was just a mistake when I was typing from, when I copy and paste, sometimes work, that's funny things like that. But they're inversely proportional. Like we said, when one increases, the one decreases. Big warning for this chapter. The speed of light is in meters per second. The wavelength is usually in micrometers or nanometers. So when you're changing frequency to wavelength or wavelength to frequency, you're going to have to make sure the units match. If they give you a wavelength in micrometers, you cannot plug it into this equation because macrometers and meters are not going to cancel out. Okay? And if you're calculating the wavelength and just have the frequency, that's going to give you the wavelength in meters, and read the question because we'll probably ask you what is a wavelength in maybe nanometers. Okay? So be very careful with the units that is the major problem my students have with this chapter. You have an example. You've seen those ugly yellow lights that you find on the streets that use sodium. The wavelength is 589 nanometers. So they want to know what is the frequency. Well, that's the question. So you can see the frequency is going to be the speed of light divided by the wavelength. The wavelength is nanometers, the speed of light is meters per second. So you change nanometers to meters. That's the conversion. Nanometers 10 to the 9, 9 nanometers in 1 meter. So once you made the conversion, now nanometers and nanometers cancels out, meters and meters cancels out, it leaves seconds minus 1, which is the correct unit for frequency. Remember, this by definition, this is the only number with significant figures, has 3, so my answer has 3 significant figures. Okay? Remember significant figures, and very, very important, because this is where most students make a mistake. You cannot cancel meters and nanometers. So you're going to have to change the nanometers to meters. Okay? Don't forget the units. Now, the electromagnetic spectrum is really a big range. It includes more than the visible. In fact, if you see the whole electromagnetic spectrum, the visible is this little part in here. Okay, it's a very small part of the spectrum. You can see as you move to the left, the energy increases, which means the frequency increases. These are the electromagnetic radiations that can be dangerous and very, very useful. Think about X-rays. X-rays can cause cancer in X-rays, but they allow you to see broken bones. We use them in PET scans and all of that. Think about ultraviolet. Ultraviolet, again, can damage your DNA and lead to cancer. When you move to the right, the energy decreases, the wavelength increases, but the frequency decreases, and you have hundreds of radiation, like radio and the cell phones. You have the infrared that only produces heat in there. But again, I want you to keep in mind there's a tremendous range of electromagnetic radiation. The visible light is only a very small part of it. Okay? These are the interference patterns that we was talking about earlier. If I could make a bigger drawing, basically we said that when the light passes, you're going to have waves passing. But some waves are going to get diffracted, so they turn sideways, and all these waves are going to start hitting against each other. So that's why you get so many different bright lights and many different intensities, because in some places the peaks are perfectly aligned and you just end up with a bigger peak. You have places where the peaks are opposite from each other, so they cancel each other and you get darkness, and you get everywhere in between. So that's why you get anything from dark to very bright and whenever the waves add to each other, we call that constructive interference. When they kind of cancel each other, we call it destructive interference. And once again, this kind of patterns, you see it only with waves, because only waves can adapt like that. So next person, Planck, he was trying to understand a little bit more about what was going on, and he figured that when atoms vibrate, they need to have quantized energy, meaning you have to have a package of energy. You cannot just have any energy, okay? There's certain numbers, and there was nothing in between. So he came up with this equation that you need to know, saying the energy in a wave is a number we're going to see that can be 1, 2, 3, 4. Planck's constant times the frequency. The energy is related to the frequency, but it's related to Planck's constant, that is this number that it will probably be given, okay? At least I give it to my students. I don't know anybody who expects people to memorize. But Planck's constant relates the energy to the frequency. The reason you have these numerals n1, 2, 3 is because what he was saying is that you have two waves, they adapt. You can move one position, and they're still adding. So there are multiples of integers. But really, even if you just memorize energy is Planck's constant times the frequency, that would be good enough for now. But that tells you that since you have specific frequencies, you're going to have specific energies. You don't have a large number of, like a gradient of energies. You just have, that's what they call it, quantized energies. Do something that was very interesting, and that was a photoelectric effect. When you have a metal, if you beam light in the metal, sometimes it releases electrons. But they realized that it depended on the frequency. Remember, the frequency is directed to the energy. It didn't matter the color, the intensity of the light, because the intensity does not tell you the energy. But the color of the light gave you the frequency, so gave you the energy. If the light did not have enough energy, it could not eject any electrons. If it has enough energy, then it emits electrons. If the frequency was more than what was necessary, the electrons came out faster. That excess energy was translated to kinetic energy in the electrons. And it didn't matter which metal it was, obviously which wavelength, depending on each metal, but for the same metal, it was the color of the light, the energy of the light, that determined whether or not electrons were emitted and how fast electrons were emitted. So that was an interesting effect. So Einstein was one who solved this. He took the simplified version of Planck's equation and he said, oh, that makes a lot of sense. Light is not only a wave. It comes in, he called it particles, but actually he's talking about packages of energy, okay, that eventually will be called photons. So for every frequency, you have a particular energy, and you have, like I said, packages of energy that are hidden in the metal. It's not a constant wave, it's just individual packages. That's why I said, you go back to the wave-particle duality. It's partially particle because you have a package, it's partially wave because you have frequency in there. When the photons have enough energy, then they expel the electron. Any excess energy becomes kinetic energy in the electrons and all of that. So light is both wave-like and particle-like. After all of these years, we are no closer to determine what light is like, right? An example of photoelectric effect in here, you have a neon sign. If you know that the wavelength is 640 nanometers, what is the energy? Well, the energy, you go back to Planck's equation, and remember Planck's times the frequency, but the frequency is directly related to the speed of light. They're giving us wavelength in here, not frequency. So that is the variation. Planck's constant should be given to you. The speed of light, you should know it. Now, once again, be careful, because the speed of light is in meters per second, and they give us the frequency in nanometers. So you have to change the nanometers to meters. And when you do that, nanometers cancels out, meters cancels out, second minus 1 cancels out, so it gives you the energy in joules. That's the energy of one photon. Okay? I know this is confusing, and if you want to make an appointment and go slower through this, if you want to practice, I have some problems. Basically, these problems, there's two simple equations. I do have a worksheet if you want to practice, but the key is go slowly, watch out for the units. Okay? But I'd be glad to meet with you. There's a link to my WhatsApp account in the video description. Make an appointment and we'll practice as much as you need so you feel comfortable before taking an exam.